let's see. Oh, just a second. I'm trying to find the controls for the, oh, there they are. Sorry about that. Yeah, I'm not really going to deal with the real basic principles of sequence stratigraphy in this particular presentation. It is a presentation that deals with sequence stratigraphy and the concept of time. Basically, what I'm going to focus on is more of the incomplete nature of the geologic record and how that impacts our studies of sequence stratigraphy. Real quickly, before I get started, I do want to give my appreciation to Petroleum Engineers Association for inviting me to do this presentation, and to my friend Pranadita Sen for making the arrangements to do this, and his company Terra Pi. Sequence stratigraphy focuses not only on the preserved depositional record, but places a great emphasis on the surfaces that separate the sedimentary deposits. In fact, a sequence itself, part of its definition is that it is bound by unconformities and their correlative conformities. And an unconformity, by definition, is going to be a surface that represents an episode of time that has either not been preserved or it was not deposited, not formed in the first place. And so the primary surface in a sequence obviously is the sequence boundary, but there are other surfaces that are also of significance, such as the transgressive surface and the maximum flooding surface. And these bound packages of sediment that we often refer to as stacking patterns that can step basinward, they can step back toward the source area, they can stack vertically. But in each case, these deposits are defined or separated by a bounding surface that represents a significant amount of time that is not recorded. An example of this can come from the Book Cliffs, where I've spent much of my time. The Book Cliffs are in Utah. They're quite a well-known area for studying sequence stratigraphy. People come from all over the world to this area to look at the sequence stratigraphy. And here's a cross section that was put together by Pattison. It's actually based on a number of studies that were done before him. But on here, you can clearly see that there are identifiable pulses, clastic wedge progradational events that step into the basin. And each one of these, so here's one down here, each one of these progrades into the basin, and then it's interrupted. There's a back step and it progrades again. There's a back step, and this continues through this entire succession. And one of the things that we need to keep in mind is that there is a significant amount of time that is not recorded or that has been removed that is between each one of these events. This can't this can't be a geology discussion without some pictures of pretty rocks. So I've thrown a few in here, but here's some actual examples. For these photographs, the one on the left, it comes from this area right here, and the one on the right comes from that zone up there. And what we're looking at here are these progradational pulses. So here's the top of a pair of sequence, progradation into the basin, relative base level rises. There's an interruption in deposition as deposition returns to the more landward area, progrades out once again. And here's another little pulse. There's the top of a pair of sequence. So each one of these represents a progradational event, a depositional event that is separated by a period of time that is not represented. Now, in this case, the one on the left, I included this one because this shows that we have missing intervals of rock, even when base level is rising. This is part of a high stand systems tract, and so during this this interval, transgressive to a high stand, and so base level is rising through this entire interval, but we still have periods of time that are not represented by strata. The one on the right shows that the We can also have missing time as base level falls. We get a forced regression. Here we actually have incision of some shoreline deposits, shore face deposits, and then base level begins to rise again, and it's backfilled. So these missing intervals of time can be developed both during episodes when base level is rising and when it is falling. We can see the effects of this in a variety of settings. Continental fluvial, such as erosional bases to channels. Even in point bars, we'll have a flooding event and then it will pause. Mud drape will be deposited on top of that. And then another flood, the point bar will migrate. And so even on this scale, there are interruptions in deposition. On the lower right, we're looking at paleosols. On the floodplain, deposition will occur, weathering will take place, develop a paleosol, more space will be created, and we get another paleosol stacked on top of that one, and so forth. Shore faces, we're very familiar with those. This is actually a transgressive or ravinement surface that we're looking at on the left, and lots of evidence here for things that would have taken place during an episode when there was a lack of sedimentation. Actually some erosion, such as the development of a ravinement surface. The lack of sediment coming in allows the surface to become populated and bioturbated, and there are a number of things that can be formed there. Even out in the marine setting, so I'm going further basinward. All these photographs are from the cliffs. Here's a thick marine section that above is interbedded with some coastal deposits, but commonly within these we'll find these resistant beds within this overall shaly succession. In more proximal areas, the resistant beds tend to be sandstone, which represent episodic pulses of sediment in the basin, probably from storms. Further out into the basin, they can actually be limestone, which is what we're looking at in this case here. And the limestone will develop when base level is high, and we're looking at sediment starvation. And so there's the ability of the carbonate particles from the organisms to accumulate and to form a condensed interval. But even at very small scale, these each one of these surfaces in here, for a surface to develop in a sedimentary deposit, there has to be a pause or at least a slowing in sedimentation. And so on a variety of scales, we're looking at situations where sediment has not been preserved. And so, back to the shore face, you can see that here. This represents a pair sequence, the flooding surface up at the top. We've talked about those a little bit. But even in the smaller scale, such as the trough cross-bedding that we find in the upper shore face, in between individual waves, there is a period of time. So these can vary from seconds to thousands of years between between successive deposits on top of one another. Okay, so to get a little bit more into the focus of the topic, this idea actually goes back quite some time. This is a paper by Barrell in 1917, where, as far as I'm aware, there may be others, but as far as I'm aware, he's the first one to suggest that the stratigraphic record actually is very incomplete. So what he did is he took a stratigraphic column. In this case, it's a hypothetical column, and he's showing the different beds that are stacked on top of one another, the different stratigraphic units. And on the right with this curve, he's trying to illustrate the importance of these surfaces that are in between the beds. So A represents the overall rise in base level that allowed the succession to be preserved. The more irregular curve represents fluctuations in base level. So it wasn't just a simple overall rise, but there were rises and falls within the larger rise, and then there were smaller rises and falls within that. So we have a variety of scales at which the sediment was deposited. And if you look at the small bed here, a sediment can only be accumulated as space is being created. And so as base level rises, accommodation is created. There is space for sediment to accumulate, and that's what's represented by this lower bed here. So notice that the rise is actually a little bit higher than the top of that bed. That's because there was a period of erosion, and part of that bed was removed, and only the basal portion was preserved. Here's a little bit bigger interval. So notice that there's a thin bed right here that represents actually this whole period of time. However, as base level rose and then base level fell, part of that bed was removed, and all that is preserved is this very small amount. So as Barrell went through this experiment, his estimate was that about 20–25% of the stratigraphic record is probably actually preserved by the deposits that we are allowed to that they were allowed to study. So I did there. Yeah, I'm going to try to draw using my trackpad. I have an iPad that I normally use, but I dropped it and I've broken it. So bear with me if these figures are not as. Oh, that's not what are not what as clear as they should be. All right. And so the idea here is that we have a sea level curve. Sea level goes up, space is produced for sediment, sea level comes down, and that space is lost, and it comes up again, and so forth. There is a limit to how high sea level can rise and sea level can fall. And so for a given area, if base level rises and then it falls, the sediment that is deposited is going to be removed and it's going to be pushed further down the basin. So for a sedimentary deposit to be preserved, what we have to have is an increase in accommodation as well. And if we add those two things together, then we increase accommodation, we lose accommodation, we increase accommodation, we lose accommodation, we increase accommodation, and so forth. And only this part of the stratigraphic record is preserved. And so what we end up, same thing over here. And so in a stratigraphic column, what we see is this part stacked on top of that part, and the upper part of the cycles are not maintained. So to visualize that a little bit better, I've actually written it out here. And so the eustatic sea level cycle rises and falls, but without some sort of subsidence, something to prevent some of that space from being removed, then we would not have a stratigraphic record. And then, so then we get cycles within cycles within cycles, and that's what we are seeing when we look at a core or a log or an outcrop. Okay, so to emphasize that once again, this little deposit at the bottom represents this small period of time plus the erosion. There's one there. So this period here, this pump has been eroded, and none of this material will be preserved into the stratigraphic record. Sylvester is probably another person I should have mentioned at the beginning in thanking for this presentation. I haven't actually spoken with him personally about this, but recently I ran across some papers that he's done. I really like the work that he has done, and I actually have replaced a lot of the figures that I have drawn myself with material from his work. So you're going to see a lot of material in here from Sylvester. What Sylvester did here is he has added another component to this scheme. First of all, there are periods that aren't only eroded, but there are periods in which there is virtually no deposition that takes place. This is he is referred to as stasis. So in developing a barrel-like curve, he's trying to indicate times when there was no deposition. There's deposition that is preserved, and then the red is where erosion has taken place. This term vacuity actually comes from Barrell, and Sylvester is using that again. And that is the part of the stratigraphic section that has been removed by the erosion. And so in dealing with time, required time to deposit these sediments, and then there was more time that was involved in removing them. And so the vacuity plus the erosion equals the amount of time that is not represented in the stratigraphic record. Okay, in this figure, Sylvester has actually redone the Barrell curve, and in this case, he's tried to distinguish between not just deposition and erosion, but preserved deposition, the vacuity, and then the period of erosion, and indicate how much each one of those parts plays in the role of preservation of the sediment. And doing this, he's found out his determination is very similar to Barrell. He believes that about for this hypothetical curve, only about 19% of time is represented by preserved strata. And so we're actually missing most of the stratigraphic record. And he did a nice little video on this. So over here on the right, notice that the stratigraphic, the deposits, they rise and they fall. We'll play that again. I know it's a little bit fast. And so deposition, erosion, deposition, erosion, deposition, erosion, back and forth through the through time. And so as we if you look at this in terms of time, then the blue is what is preserved. That's what we actually see in the rock record, the gray and the red. The gray is what was deposited and removed, and the red is the process of removing that sediment. Okay. So with that, I want to put a couple of these diagrams together. Okay, first we'll start here with the curve that we were looking at before. And then here is a basin floor, and here is an original. Here's where we're going to start with sea level. So if sea level starts to drop, what we're going to see is that above sea level over here, we have erosion that's taking place. And the sediment that is eroded from right here is going to be deposited. The coarser clastics here, and the way out in the basin will get the fine sediment. But as base level continues to fall, we're going to see a downstepping of these parasequences. And so what we're looking at, if we go over here, here's the high stand. This little point right here is the maximum rate of fall. Okay, and this is the showing us the area that's being eroded, and we tend to refer to this right here as the falling stage systems tract. The falling stage systems tract represents a forced regression. I'm just going to abbreviate things here. It's represented by a progradational pair sequence set that offlaps from the prior the prior pair sequence. And so if we look at that over into this area here, so this zone here on this sea level curve is going to represent the following stage systems tract. Okay, down at the once we get to this point here, we're looking at low stand. So here's high stand. This is as low as the relative sea level or base level gets. So at this point, base level starts to rise, but is rising relatively slowly. And so the pattern that we're going to see out here in the basin is that we're going to see a change from this downstepping progradational pattern to more of a vertical building. And that's going to continue until we've got a little point here that's called the maximum rate of rise. And it's going to be bound on each side. And this area here is where accommodation, well, first of all, I should have mentioned that on this one over here, accommodation is negative. We now have positive accommodation. Accommodation is being produced, but it's being produced relatively slowly. And so we're looking at a situation here. This is the low stand systems tract, where accommodation is roughly equal to the sediment supply. It's characterized by an aggradational parasequence set. Okay, when we cross this boundary here, this is the transgressive surface. This is a period of time where the rate of accommodation now becomes greater than the rate of sediment supply, and we begin to see a backstepping pattern in the parasequence set. And we call this the transgressive systems. Sorry about the writing there. The transgressive systems tract. And here we're looking at a retrogradational parasequence stacking pattern. And then as we, this other surface up here, which we refer to as the maximum flooding surface, this is where we start to see a turnaround. And the sediment supply again becomes equal to the rate of accommodation. So we go back into an aggradational pattern, and then as it continues to slow down, it will transform once more into a progradational pattern. And this is our high stand systems tract, which is characterized by a progradational parasequence, well, aggradational to progradational parasequence sets. And so high stand right here. Okay, now the reason I wanted to go through this little illustration here, and again, I apologize for the artwork. I actually have had students tell me on the course evaluations to take it on a class, but I'm usually not drawing with the trackpad. The point is that whether we're involved in a forced regression, in vertical stacking, in rapid transgression, or in slowing transgression into progradation, each one of these units represents a parasequence and there's going to be a significant amount of time that is missing between each one of those. And so to illustrate that a little bit more nicely, on the left, here's the sea level curve with the different parts, and then on the right is an idealized sequence showing the different systems tracks, and then over here you can see where they would relate to the sea level curve. And so whether we're prograding, ugrading, or retrograding, each one of these surfaces represents a period for which there is no depositional record. Okay, so that takes us to the next step here. Most of you are probably familiar with the Wheeler diagram, which was published in 1964 by Harry Wheeler. And in here, this was an attempt to re-plot stratigraphic cross sections in terms of time rather than physical stratigraphy, actually, at least on the vertical axis. We're still looking at distance on the horizontal axis, but on the vertical axis, we're looking at time. And so the example that he has given here is there's an angular unconformity. And obviously, there is more time that is missing from the lower beds that have been eroded than from the upper beds. And if you take that and you straighten it out, you're going to end up with this triangular shape that demonstrates that in a landward direction, the amount of time that is represented by that unconformity surface. So this is one unconformity surface that runs across this entire length. And out here it becomes a correlative conformity. We call it a continuity. But this one surface is not going to represent the same amount of missing strata or unrepresented geologic time from one side to the other. So in the proximal part, there is a much greater gap in time than there is in the more distal part of the basin, where then again it transitions into the what we now call a correlative conformity. And so what Wheeler did, this is an example of an exercise that is commonly used for this today. What Wheeler did with this was he identified timelines, and those timelines. So here's time one. You would come all the way down here to time one that is represented on the vertical axis, and you'd mark the boundary, and you do the same thing with the other side. And as you do this with each of the timelines, you will end up with a figure similar to the one that's on the left. It was done by Vail et al. in 1977. And so here is a preserved stratigraphic record. And if it is replotted in terms of time rather than physical stratigraphy, we see that there are large gaps for which there are no sediment present. And an interesting thing about this diagram is notice that the unconformities on the left are offset. They're out of phase with the unconformities that are present on the right. And so on the left, we're removing deposits as well as periods for which there is no deposition. There's an actual erosion that is going to be greater on the left-hand side than it is for the right, where it becomes a correlative conformity. Now, out here in the basin, we really don't see a lot of erosion. So what is going to be responsible for these gaps in the depositional record? Out here, it's more likely to be related to non-deposition, the sediment starvation as base level rises. And here's another example of this from a seismic section on the right. You can see the large gaps on the left proximally, and they're on the right distally. Again, Sylvester took the Wheeler diagram, and he ran it through his computer simulation, and he's got initially he shows actually sediment was deposited here, but it was later removed, so he calls this the vacuity. The hiatus is where deposition never took place. This is the time that the lower material was being eroded, and he's been able to recreate the triangle from the from the Barrell curve. And I'll show this little video off to the side. Okay, so this comes. I want to emphasize a little bit more the timing of the discontinuities. In this case, the photograph you're looking at here comes from Palisades Reservoir in Idaho. In this particular year, we had a very high snowpack, and there was a lot of concern over flooding and overfilling the reservoir. So, in anticipation to catching all of that runoff, they lowered the reservoir. In fact, they nearly emptied it. And the interesting thing in this photo is if you look off in the middle part, the upper part of the stream, you can actually see that erosion is taking place. These deposits have been cut through. And while they're being cut through, while the reservoir is being lowered, that sediment, the coarser part of the sediment, is forming the parasequences that we typically talk about in sequence stratigraphy here along the delta front. But then out into the basin, deposition is continuous. So erosion, and out here continuous deposition. And so back to a figure. If you look at here's our basin. Once again, and we put sea level over here. Okay, as sea level falls, erosion is going to take place in this area. We're going to form the parasequences that we discussed. But then out here further in the basin, the sediment that is being carried by suspension is going to settle and is going to form a continuous record. However, if sea level then were to rise, what that's going to do is then these are going to backstep, and the fine grain sediment is going to migrate landward, and out here we will get an unconformity that is not due to erosion, but rather is due to a lack of deposition, to sediment starvation. So the unconformities here and here are formed out of phase with one another. They're at different times in the stratigraphic record. And so again, you can see that here, erosion in this area, and deposition is taking place out here. And so if we go back to this diagram here, this area is caused by erosion during base level fall. And these unconformities out here are the result of non-deposition during and sediment starvation during base level rise. One more example of this. This is an exercise that we did with my geomorphology class at BYU, Idaho. We were actually trying to create a meandering channel, which we didn't do in this case. We did with later experiments. We found out that this stream table was actually a little bit too small for that. So we changed the experiment and decided to see if we could recreate a stratigraphic sequence. And we started with base level about where you see it right now. And then we dropped it in 3 steps, down to about here, and then down to there. Now the lower pulses you really can't see because they're buried by what we see here. But as we drop base level, it incised a much deeper channel than what we had before. It created a small delta here, and then another delta that was offlapping that one, and then the third delta that was further out into the basin. Then we did the opposite, and we started to rise. So that would have been the falling stage systems tract. So we thought, let's see if we could create a low stand systems tract, and we started to raise base level. And again, this one you can't see; it's buried by here, but that might be it right there. A delta that formed on top of the, maybe that's it right here. That formed on top of the others, and then we increased the rate of base level rise, and you can actually see the backstepping pattern here. So here's the low stand delta and the transgressive systems tract as we move back through. But each one of these, when we rose base level, deposition had to start over again and work its way out into the basin. And so there is an unconformity that's at the base of each one of these lobes that you see within this delta. When we raised base level back to its original elevation, then we developed an incised channel fill. The channel became filled with sand, and when it really couldn't be transported any further, it began to overflow the banks and produce essentially alluvial fans in the more proximal area. Okay, but during this time, as base level was dropping, you can see the muddy sediment out here. There was a continuous rate of deposition out in the further out into the basin, and if you look really carefully along the margin of these, you can see little mud drapes that were preserved as the backstepping took place, and that fine-grained sediment began to, rather than being transported all the way out into the basin, to be deposited onto these lobes. Peter Vail and the people that he worked with at Exxon took this another step, and they decided to see if they could use these gaps in time, these unconformities, to identify eustatic sea level cycles, to see if we could distinguish between local and regional events and events that were on a global scale. And they did this by identifying erosional surfaces, sequence boundaries, maximum flooding surfaces, and dating those and seeing if they could correlate them on a global scale, and to distinguish between sea level changes that happen simultaneously across the world from others. And I'm not going to say much more about that right here. Okay, the last thing that I want to emphasize here is the different record that will be recorded depending on where you are within the basin. On the left, you might have heard of the XES Basin. They used to call it Jurassic Tank, University of Minnesota, a very large stream table wave tank. They can do a number of things with it. They have it designed so that they can control and change the rate of sediment input, the discharge. They can also lower and raise. Okay, they can lower and raise base level, but they can also lower and raise the basin floor to represent tectonics. And so what they've done with this experiment here is basically modeling a passive margin in which there is a hinge. The basin is deepening out away from the source area. They hold this at a constant sedimentation rate and a constant subsidence rate. And what they did through the experiment is they varied base level. Base level would rise, base level would fall. Some intervals they would raise base level rapidly, others they would raise it slowly, and the same with the fall. Here is a map of the surface of the tank, and there are 3 dots here. You'll notice that each one moving downward is a little bit further out into the basin than the one before. So if you look at this in terms of a cross section, the first dot, second dot, and third dot, up here is a dip cross section through their final deposit. The one below is a strike section. And what is interesting about this, and here's where Sylvester was involved again, is he took the XES experiment and he applied to it a Barrell curve. And so by doing this, he's identified where in this figure we have preserved sedimentation, we have the vacuities, and we have the times of erosion. And from that, he estimates the amount of section that is preserved. But what is interesting is how this changes from proximal to distal across the cross section. And the importance of this is if you're trying to correlate the surfaces in the basin with those that are in this would be the more fluvial realm, and over here would be the shoreline, and out here is the deeper basin. You're going to see it's going to be actually fairly difficult to correlate these, as the unconformities become the correlative conformities. So as we would anticipate, in the proximal area where base level comes into contact with the shoreline, as it rises and falls, we're going to see significant episodes of deposition and also of erosion, and much of the sediment that was originally deposited is going to be removed, and we're going to have a very incomplete stratigraphic record that is present. And you can do so up here. If you look in the upper left-hand corner, in this case we have about 15% of the stratigraphic record that is preserved in the fluvial part of the section. As we move out into the coastal area, excuse me, this dot right here, notice that we still have significant erosional events, but they're not nearly as deep or nearly as long as the ones that we saw in the more proximal area. So we still have significant unconformities, and this is where we do a lot of our sequence stratigraphy is right here in the coastal area. And then further out into the basin, we're seeing almost no erosion. Here we're consistently below sea level, base level. Base level never drops low enough to actually remove sediment. But instead, what we're seeing in this area are these periods of stasis of non-deposition. So we still have intervals in which there is very little sediment that's being preserved as part of the rock record, but rather than being removed, it simply is not deposited. And so you can see that would be a challenge to correlate between these three areas. I noticed that the rate at which sediment is preserved increases from 15% to about 36% to 38% a little bit further out in the basin. Again, here it's deposited and removed, and down here it's not. It simply is not deposited. And so to look at this just a little further, this is the same experiment. In this case, Sylvester has added to it the Wheeler diagram, and with the Wheeler diagram, we've got the sea level curve and the raised base level slowly, and the drop is slowly, and here they raised and lowered it very quickly, rapid succession. But notice again that in proximal areas, very big gaps that decrease basinward, and from the basinal areas, they decrease landward. The red represents time of erosion, and as would be expected, right here at the terminus of the erosion is the greatest amount of sedimentation. It decreases basinward. Here, they put together some maps that show deposition in terms of both time and thickness, and as you would expect, the amount of time over which deposition takes place is going to increase from land out into the basin. And the opposite is also true, that the amount of erosion is going to decrease from the land out into the basin, and we can just combine the erosion and the vacuity, because the erosion is removing the sediment that was here. Now, it's interesting to see, though, that there's a difference in the depositional thickness. So this one represents time. And over here, we're looking at thickness. Very little sediment is preserved in the continental realm, but there's also not a lot of sediment that is preserved in the deeper marine realm. Here in the middle is where you have the greatest thickness of sediment. And this goes back to that alternating out of phase unconformity characteristic: deposited and eroded, not deposited over intervals of time. And in the middle is where you have the most continuous deposition that is taking place. So even though the amount of erosion decreases basinward, the thickness of deposition is going to be greater at the terminus of the zones that are being eroded over in the proximal area. And then in terms of the geometry of the unconformities, so again, we've got here a strike section, a dip section, and then a strike section. And the Wheeler diagrams that belong to both of them, as we've mentioned before, there's a greater amount of erosion that decreases basinward in the dip section. There's non-deposition that increases deposition toward the land from the marine section. If we're looking at the strike section, these are pretty much horizontal, because we're looking along the coast rather than from land out into the basin. But also, something to keep in mind is that, especially here in the continental portion, we're going to see a change in the location of the deposcenter. So the erosional surface is going to migrate back and forth from the input source, and then excuse me, but also even out into the basin. This is where the deltas are located. There'll be a deposition here while there's very little up above. Then the river is going to shift into a deposition here and very little down here. And we're going to see the shifting delta lobes. So deposition, then that will subside, and it will move back and forth. And the result, it's a little bit harder to see here than what I anticipated, but in this diagram right here, you can see these erosional surfaces. They're not flat and planar in depositional strike, but they deepen and then they rise. And this represents that channel and the delta migrating laterally back and forth, forming a very irregular surface. So even along the coast, we may not be able to correlate, at least on the smaller scale, as much as we often think that we can. And to show this in video form, so that's the dip section. We're on the strike section. Yeah, play that once more. Yep. That's right. And by the way, if you want to see these videos and others, I've included the website here that you can go to, and this is actually a YouTube presentation that Sylvester has given. So again, I use a lot of his work in here, and appreciate what he's done. Okay. Now, normally at this point, what I would do is that's pretty much the lecture that I wanted to present today. I want to leave a little bit of time for questions, so I'm not going to talk much longer here. But at this point, if we were doing this in a classroom setting, then we would now do a couple of exercises. This is one. It's the diagram I showed before, where you would actually create a Wheeler diagram from this hypothetical cross section. This is a very common exercise that is done by many. And so with that, I will go ahead and turn the time back over.